Okay, welcome back. So now we have lots of K's, and we are about to work with one of the three of the last K's that exist, and that is the Ka. And the Ka helps for weak acids, and it helps explain the difference between strong and weak acids. So strong acids, and in the first review session, we went over the strong acids. Completely dissociate into ions. So they completely go in this direction. There's no equilibrium, so you can't really write a Ka for strong acids, because there really is no. These reactions go to completion. They completely lose their H+. But if you had to write a K, you would say the K is huge, or very much bigger than 1. Whereas weak acids very slightly dissociate into H. So the reaction would lay more towards this part of the undissociated, of this not losing its H. The equilibrium would lay this in that direction. And the K would be less than 1. Or the Ka would be less than 1. Now we write Kas just the same way as we write Keqs. The products go on the top, and the reactants go on the bottom. We do not include water because it's a liquid. So you can see that this is the, these are the base, so they go on top. And this is the reactant, it goes on bottom. You could also just have H+ here, because remember, hydronium and H+ are interchangeable. So again, this is just showing the same thing in pictures, and again, the picture's not that great. But if you have a strong acid, okay, and you put it in water, none of it is going to be left in the undissociated form. All of it is going to be dissociated into H+ and the conjugate base, or the anion in this case. I'm sorry, not the conjugate base, the anion that it dissociates into. So yeah, I guess it is its conjugate base. So what will be left is this guy, and its conjugate base. This is what this comp becomes after it loses its H+, so that is its conjugate base. Now, so it completely dissociates. There's none of the acid in the undissociated form left. Okay, and this is the strong acid list that we talked about. I'm not going to go through it again, but you do need to memorize that these are the strong acids, especially this column and these two. These are the ones that they like. So these are the strong acids. All the other acids that you see, and you can identify something as an acid if it has an H in front, or if they say it's an acid. Are considered weak. So this is a little bit different. So this is the dissociation of weak acids. So you see, if you're adding it to water, what's going to happen is most of it stays in the acid form. It only loses a little bit of its H, and less of it has lost its H, so therefore there's less of the conjugate base. So you have more present in the non-dissociated form here, if it's a weak acid. Okay, so the stronger the acid, the higher the Ka. So if you have a general reaction, so we have the acid plus water will produce hydronium ion plus the anion, right? So the higher the Ka, okay, remember that means when the Ka is bigger, that means the reaction will go further this way. The bigger the Ka, and that means it will release more H+, or there'll be more hydronium in the solution. So the bigger the Ka, the more forward the reaction goes, in this case, because remember, it's also products over reactants, so if you're getting more of the H+, then the products are going to be bigger, and you'll have a higher Ka. Now, Kas are annoying numbers to write, because they're, like, usually in scientific notation and very small. So chemists have called something called pKa, okay, which makes the numbers easier to deal with, and I'm going to talk about pKa in a second. But the formula is that pKa is equal to the negative log base 10 of the Ka, and we're going to practice with this formula in the next slide, and sort of relate how does the pKa relate to the Ka. But again, I believe this formula is on your formula sheet, but if it's not, we'll talk about it. I don't have the formula sheet with me right now. Wait, I have it right here. Hold on, let me pause video. It is indeed on your formula sheet. It's actually the last formula in the equilibrium section, so you can go look if you want. We are now going to practice with the Ka, and you have a blank slide to practice on, so I'm just going to practice underneath, but you have a blank slide. So it says, write the reaction of acetic acid with water. So we would have H2O and acetic acid, which is vinegar. Notice the H in front. Okay, and it's acting like an acid, so it's going to lose that H in front. And when it loses an H, it becomes negative, and then the H is going to hop onto water and become the hydronium ion. And then we're also going to do the same thing for nitrous acid, which is not nitric acid, so it's also a weak acid. So we have water, and you might want to try to do this one by yourself to see if you get a hang of it. And we get NO3 minus, and the H hops onto the water to get the hydronium ion, which is plus. And then we're going to write the Ka for each of them. So I'll write the Ka for this one in this color. So the Ka, remember, products over reactants. So the Ka would be the concentration of C2H3O2 minus times the hydronium concentration. This is plus over, remember we don't include water, the undissociated acid. And my phone is going crazy. It's probably one of you guys contacting me. And I'll write the Ka for the other one in blue. So we have Ka, again, concentration of, this is the conjugate base, minus, plus the hydronium ion, oh, not plus, times, it's all multiplication, over the non-dissociated acid, and this should be a 2, because I'm an idiot. I voted as a strong acid, which this equilibrium wouldn't exist then if it was a strong acid. So there we go. That should be an N. So those are our Kas. So we did 1, 2, N. This is number 3. So let's see what number 4 holds in store for us. So the Ka for acetic acid is 1.8 times 10 to the negative 5, and the Ka for nitric acid is 1.7 times 10 to the negative 4, which is the stronger acid. Explain. So the one with the stronger acid is the larger Ka. So nitric acid is the larger Ka. And what that means is that since the Ka is larger, there are more products. So since there's more of this, or more of the H plus, or more of the hydronium ion, and you can write this down, I'm not going to. So again, this is a larger Ka, so that means there's more products, or these are higher. There's more products produced in the reaction, so then there's greater H plus or greater hydronium ion. So therefore, it's a stronger acid. So now we're going to calculate the pKa for each. So remember, pKa is equal to the negative log of the Ka. So we're just going to, for each one, we're just going to negative log the Ka. So I will need a calculator. So hold on, let me grab a calculator. So essentially, for each one, you're just going to take the log of the Ka. And then make it negative, and that equals the pKa. So for the acetic acid, so negative log of, and I gotta look at the number because I'm running out of space. Negative log of 1.8 times 10 to the negative 5th. So the log button is above the natural log button if you're doing it on my calculator. 1.8 second e to the negative 5. And I get pKa, and you just make it, pKa is always positive, so it would be positive 4.7 if it's 2 sig figs. And then we're going to do the same thing for the other one, so this is for acetic acid, and this is for nitrous acid, so pKa, again, equals the negative log of the Ka, so pKa is equal to log, remember it's negative, and I gotta get the Ka, 1.7 times 1.7.1. Did I write that right? Yep. Times 10 to the negative times 10 to the negative 4, and then we button press, and we get pKa equals 3.1 with if it was 2 sig figs. So notice that a substance that is a stronger acid has a lower pKa, which is always confusing to people. But the numbers are nicer to deal with. So again, something that is a strong acid, so lower the pKa, stronger the acid. which is the opposite of Ka, but again, we like to deal with pKa's because they're nicer numbers than in terms of the ones in scientific notation. So there's also a Kb, and the Kb is sort of the same as the Ka, except it's 4 bases, and the same sort of rules apply. So you can see, again, we don't include the water, and we have the products over the reactants. And the same rules apply. The larger the Ka, the stronger the base. So in terms of bases, you'll have more of the water in the OH form. Or you'll have more products or more things that have accepted H+. We generally deal with more with Ka than Kb. But there is a Kb. And let me hold on for a second. So since I already did this, I might as well use it. So it says, write the balanced equation for the ionization of weak acids, pyritidine, in water. So here's the acid with water. Here's the base with water. Remember, bases accept H+, so it's going to get a 6 here, and it's going to become positive. And then, so there is it positive, and then the H came from the water, so the H becomes OH minus. And then again, here is the Kb expression. We have the products over the reactants, and remember, we don't include water because it's a liquid. So again, remember bases, they gain H+, so this becomes a 6 and gets a plus, and it's getting the H+ from the water. So who are the weak bases that we talk about? So we talked about weak acids generally having the formula with an H in front and some random thing. Well, weak bases generally have some stuff, and either N, NH, or NH2 at the end. So these are examples of some weak bases. Remember, the strong acids generally have OH in them. So we identified the strong bases in the review session. Okay, so now this is really, 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 really important. So, and I have 3 minutes to do it, or 4 minutes to do it, so let's go. So a strong acid, when it dissociates, has a pathetic conjugate base, meaning it doesn't really act at all like a base. Whereas a weak acid, a stronger weak acid, has a very weak conjugate base. Whereas a weaker weak acid has a stronger conjugate weak base. So in other words, the weaker the acid, the stronger its conjugate base. I would write that down. The weaker the acid, the stronger its conjugate base. And on the opposite side, strong bases have pathetic conjugate acids, and we're going to do acids, and we're going to do a little bit more with this in CAS, which they actually don't even act like acids. So you can see here, HCl is a strong acid. Its conjugate base doesn't even act like a base. Like, it can't really even accept H+. And as you go down, these acids get weaker as you go down. So for example, this is an acid. Its conjugate base is stronger than, let's say, Cl, which barely acts as a base. And again, we're going to practice more of this in class on Monday. So this is the last thing that we're doing. I said this, I might have cut off. This is the last thing that we're doing, and then you're going to do the second example as homework and take a picture and submit it. Okay, so we're going to first identify the acid and base pairs. So this is losing an H, this guy is losing an H+, so this is the acid, and this is the conjugate base, and then this is acting like a base, and this is the conjugate acid. So we did that part. So it says now, the K for this reaction is very, very small. So that means this is a very, very weak acid. Okay, that means it's a very, very weak acid. So since it's a very weak acid, it produces a strong conjugate base. So this conjugate base is strong, and it's weaker than the base here. So this one is the first, in terms of bases, this would have a higher Kb than this one. The Kb decreases as you go down. Similarly, HF would be a stronger acid than H2S. Again, the reason that is that the reaction equilibrium, since K is very small, lies all the way to the left. So this would be the stronger acid, and this would be the stronger base, because the equilibrium lies to the left. So these guys, the reaction's going to go this way, and these guys are going to lose the H+, and this one's going to gain the H+, and act like a base.